Hello, the internet, and welcome to Open Source Directions, hosted by Quansight, the webinar that brings you all of the news about the future of your favorite open source projects. My name is Anthony Skopatz, your host for Open Source Directions. Co-hosting with me today is Medican.
Hi, I'm Medican. I'm really excited to be co-hosting today with you, Anthony. I'm a postdoc at the University of Illinois
I'm
at
Sean
Urbana-Champaign, and I'm currently located in Champaign-Urbana,
scientist working
and I work on a
the
project
exploration
called
lab team at a TD Ameritrade. So we explore new and emerging technologies, might help the company differentiate ourselves from our competitors. And before we get going too far, I just want to remind everybody that I'm actually not a time series expert by any means, but Stumpy just happens to be one of these explorations that I was able to take into the open source with the company.
Excellent. Thanks. Thanks, Sean. We're really excited to have you on today and excited to hear about Stumpy. But before we get into that, we like to do a brief personalization section. So this week we have the Tweet of the Week section, where each of us today will share a tweet that we've been enjoying recently. So Sean, you are first up as our special guest.
Tweet of the week is that, we all know, or some of us might know, that the SciPy conference being held in Austin, Texas this summer, July 6th to, I think, July 12th, is happening. And the call for proposals has been out there, and there's been proposals trickling in. So if you're interested in participating, do get your proposals out there. Deadlines, I think it's beginning of February.
Yep. Great. Thank you so much, Sean. Yeah, that great plug. Medica, your tweet.
Yeah. Okay, so I want to give a background on my tweet, which is every once in a while I go through Twitter just looking for cat stuff because in addition to my love of Europop, I love cats. And so this tweet is old, but I love it anyway. And it's an imagined conversation between Salvador Dali and Remedios Varo, who are both surrealist artists. And so the conversation is between them. Dali says, surrealism is destructive, but it destroys only what it considers to be shackles limiting your vision. And Vara's like, I'm envisioning some cats right now, smiley face. Dali says, that's not what I meant. And Vara's like, they have their own little castle and everything. And then it's a picture of one of her paintings, which has all these like extremely happy cats in a castle.
For my tweet,
and it's so weird, but so amazing. So I hope you all enjoy it.
Says, a lot of information about color palettes for various uses, including colorblind users, is at the following link. So I encourage folks to, especially if they're more on the design side or you're trying to design something, please keep in mind the colorblind users out there. Always good to think about accessibility with these things, with our software projects. And with that, we'll go ahead and transition and talk about Stumpy. So Stumpy's been around for, I think, around a year now or so. It's got about 1,000 stars on GitHub right now and receives about 1,500 downloads between PyAPI and Conda every month. And so we're just going to go back and forth and ask a few questions about the project and have a little conversation.
Yeah, cool. So it's been really cool to see Stumpy growing.
Yeah, so we've been
seeing all those, hearing about all those stats, Sean. Can you tell us a little bit about
really,
why this project
where this all started from
and
was,
what need it
I guess
fills?
back when I was a postdoc and doing my PhD, I dealt a lot with time series data, so doing computer simulations. And there are a lot of classical methods for approaching sort of analysis of time series. You can visualize it. You can do some looking at mins and maxes, right? Means, deviations, variances. And then you can take it a step further. You might build ARIMA models, or you might even build some sort of Markov models, right? But these are very classical type approaches. And what I noticed was that there really wasn't any modern approach, right? There's no textbook way where, given a brand new time series, use some method and it will just tell you where you should start looking first. Right? It might not tell you where, everywhere to look, but it at least help you hone in on this. And in terms of other sort of recent time series type tools. Obviously, there's the machine learning and the deep learnings of the world, but oftentimes those are fairly black box. They often don't actually tell you much about the data itself. You're just building a model typically for prediction, right? In this case, when you have data, people will say, look at it, but when the data beyond maybe even a few thousand data points, it becomes unmanageable, right? So we have to think about how might we start analyzing this type of data. I wanted to give a shout out to maybe Facebook Profit, which is good time series forecasting. At the same time, that's been at least one advancement in time series analysis. But Stumpy actually serves this need of, given a brand new time series data, either where you don't have domain expertise or simply too big for you to visualize or analyze using classical methods, what might you do, right? And so that's where it was born out of. And I've seen this time and time again. Even when I go volunteer for like a data hackathon, usually the data that gets dumped in front of me is, here, this is about, I don't know, fishing or something, right? And I'm not a domain expert. And I don't even know where to start looking first. If only there was a way that I could take this data, pump it in through some algorithm that just directs me and focus my attention.
Yeah, it's great to have a high performance generic time series toolkit out there. But I'm curious, where did the name Stumpy come from?
Yeah, that's a great question. So Stumpy is actually based on some academic research coming out of UC Riverside. So at the end of the fall of 2016, they had published a series of back-to-back papers that I just happened to stumble across on Reddit. Actually, the corresponding author posted it on, and it's a very obscure name. They called this the result of this analysis something called the matrix profile, which we'll get into later. But I read the paper and I started playing around with it, implemented it in NumPy or NumPy, if you will, and actually what happened was in the paper, the algorithms for computing this thing called the matrix profile. The algorithms were called Stamp, and then they had a second generation algorithm called Stomp, right? And then naturally, when I was looking for a name for Stumpy, right, I thought Stump, right, or right. But also there's a couple of other reasons, right? So the U or the UM part of it sort of pays a little bit of respect and homage to the fact that we're using NumPy, we're using Numba for parallelization and CUDA compilation of code. But as well, a lot of people might not know this. So I'm based out of Ann Arbor, Michigan. It's actually known as Tree Town or Tree City, USA. Right. And so that all sort of ties in. And if anybody's ever pulled up the stump, you actually see that it is a cross section of a tree stump with data points coming out of it. So it's designed actually by our internal design team, taking a lot of these ideas and keeping them in mind.
Oh.
I say Stumpy because
that's really cool. And
word.
I guess now you've given us a hint
Stumpy,
of what the preferred pronunciation is,
or other people. Yeah, I would. So of course the original
are there any other
researchers at the University of California, they have their
touched a little bit on this, but I'm very curious.
A lot of the earlier versions that they had were written in MATLAB, not really that approachable. And then later on, the more performant code they have in C and CUDA. But obviously, for sort of the scientific Python or PyData or data scientists, right, that might not have a lot of coding experience, a lot of that tends to be maybe less approachable. And so what I did was verified that their sort of algorithms actually work, and then ported them over into performant Python code, right? And in addition to that, there is sort of other projects, open source projects that do calculate this thing called the matrix profile, which is at the core of Stumpy. But there's a Go version, a Python version. You can even find an R version. But for a Stumpy specifically, our focus is on ease of installation, right? So hopefully within 30 seconds less, you can either conda install it or pip install it, and you should be ready to go. But also performance, right? So being able to scale up to, I've scaled it up to as many as 256 CPU cores,
Mm-hmm.
or even to 16 GPUs, right? So you can leverage all of the compute power. I like to joke around that when your deep learning models are idle, or your GPUs are free, you should use Stumpy, right? Keep your house warm.
Yeah, could definitely use that in up here in the Northeast, the suite. So what technology is Stumpy built on? You kind of hinted at this, but maybe there's parts we're missing.
Yeah, and I think this is actually very, very right. So we try to focus on meeting the users where they're at. A lot of our users will be data scientists, and chances are, if you're a data scientist, you're going to be in the Python world, right? You're going to be using NumPy. And so Stumpy only has 3 dependencies, hard dependencies, and that's NumPy, SciPy, and then the last one is Numba. So Numba allows us to parallelize our code to multiple CPUs, but it also Numba compiles down to CUDA as well. So having only 3 dependencies is the major thing. We do depend, we have soft dependencies if we want to scale on the CPU side to multiple servers, so that the dependency there is to use Dask for parallelization. But in the future, if we're thinking about multi-GPUs across multiple servers, that will likely leverage Dask as well. So that's probably part of the roadmap talk. As well, we have we have support for pandas data frames, so not only NumPy arrays, and thanks to folks like Anthony and the rest of the Conda Forge team, we do a lot of our packaging through Conda Forge, and also Azure pipelines for all of our continuous integration.
That's awesome. I also noticed on your GitHub profile that you have 100% test coverage, which is like wild and really exciting.
Yeah, so that was me.
Can you tell me
being on this
who started specifically
here at TD Ameritrade,
the
our goal is
project,
to find
the
these
Python
very
version?
sort of weird niche things, right, that maybe other people aren't looking at. And so when I stumbled across this concept of computing a matrix profile, I thought these papers just sounded too good to be true. Right? It was like a dream come true. And usually when it's too good to be true, it probably is, right? But it turned. So I wrote some initial code in January of 2017, and within a very short period of time, got it all up and running. And then when I started thinking about how might we share this, like this is actually very, very useful. I thought, how do we share this with the rest of the world? And that's when I started thinking about scalability, to make sure that you start using it and say, you know what, it's a fun toy concept, but it doesn't scale, right? It's not performant enough. But at the same time, we're not looking at extreme scalability either, right? It doesn't have to be the fastest implementation. Although I will tell you that compared to some of the other open source packages, it is extremely performant. Maybe compared to the researchers' sort of raw C or CUDA implementations, we do take a bit of a hit, but we're constantly moving. And look at the Stumpy website, you'll see our performance comparisons, and we scale very well.
Excellent. So who maintains Stumpy?
Right now, I'm basically the core maintainer and developer. I'm fairly active, but at the same time, as Madikin pointed out, because from the get-go, from day one, we knew that we wanted to open source this. So I spent a lot of time making sure that the test coverage and the amount of unit tests that we have in there are very, very complete. And this makes it a lot easier, and not as sort of like a hindsight kind of deal, right? Where people want to contribute. It's fairly simple. Submit a pull request, and if the tests fail, right, then we'll have to address that first. But if they pass, then that's great, right? And we also want to make sure that we're writing unit tests for everything that we do. And so we've kept that up, and actually it saved my life a couple of times too, where we've all experienced the late night coding, where you just start losing, right? And this unit test really just helped keep my sanity.
Yeah, it makes sense.
Yeah, that's super, yeah, I mean, that's super nice. And it also is nice that you're, thinking about people contributing and making it a little bit easier for them to see how things are working within the code. So related to that, can you tell me what communities your users and your contributors are coming from? You mentioned data science a little bit before, but
we're still
is
fairly
it
new,
broader than that?
right? So even though we've got about
14,000 users and contributors,
downloads of our software, it's one of those things where if people use it and they're successful at using it, they have no need to come back to us to tell us what they're using it for. At the same time, if it's not what they need, right, they'll quickly move on. But we do occasionally get some feedback in terms of what users are using it for. For ourselves, you can imagine, because Stumpy is completely data agnostic or domain agnostic, you can use it for any time series data, right? Whether it's for IoT, oftentimes we might think about using it for monitoring, right? Maybe like CPU, RAM usage, and what might be a pattern for identifying that a system or server might go down. You can think about for me, I'm in the finance sector, so you can think about things in terms of financial time series. So looking at stocks, right, and analyzing that. We actually had recently a conference for looking at cryptocurrency, so Bitcoins, and how the cryptocurrency is moving. And so leveraging Stumpy along with deep learning in combination, and showed that when you add matrix profiles along with these LSTM models, it actually reduced their error by about 8%, just out of the box. So a lot of fun.
That's incredible.
Wow.
That's awesome. So is the project or Stumpy participating in any diversity and inclusion efforts currently?
So not explicitly. Again, as I mentioned earlier, so new. Oftentimes I don't actually know who my users are. There are things that we put into place. Obviously, from the get-go, once we open sourced it, we made sure to have a code of conduct. And to make sure that, as we're conversing with people who are contributing, people who are asking questions about the usage of Stumpy, that we ensure that our language is appropriate, right? That we're professional, and that we don't assume any sort of experience, right? You come in, you ask a question, we try to find out where we can help you, and that's really important for us. And we also make sure that our language that we use is thoughtful and mindful that people are coming from many different backgrounds.
Yeah, that makes a lot of sense, especially for newer projects. It's there's a big learning curve on all of this stuff. I think you're starting off in the right spot with code of conduct, etc.
Yeah, it's really challenging. So it definitely sounds like you have the right steps.
So at this point, we're going to get into the really exciting demo section of the webinar. So I believe, Sean, that you have some things that you want to show off here for Stumpy. And, we have the docs here that Brandon will link in the chat. And I think there might be even a motivational video, which is kind of fun, but we're not going to watch that. That's a homework assignment for this year. So, if you want to share.
Yeah, definitely.
Yeah.
So if everybody can see this, so this is the Stumpy documentation. So as Anthony mentioned, there is some background motivation. It's not so much of a motivational speech, but about I gave earlier about really the longer form of how Stumpy came to be and really the background, right? But as I mentioned earlier, there is tutorials here. This and explain what this concept is of a matrix profile in relationship to a time series. Imagine if you have this time series that you're seeing here, right? Just data points. So anything is the length of this. I can plot it just like I mentioned earlier. You can visualize this, right? If I asked you, is there a pattern that you might see in this, right? Something or any anomalies, you might be able to spot it that maybe something out here might be anomalous or there might be some pattern in here. But how might we start analyzing this? So the one thing that we can do is we can take this time series and we can define something called a subsequence. And a subsequence is nothing but a part of the full time series. So in this case, This is a subsequence of length 2, so that could be a subsequence of the entire time series. This is a subsequence of length 3. Straightforward. And then in this case, I think this is a subsequence of length 8, right? So it's kind of arbitrary. So you can choose these subsequences, and what you can do is you can start comparing part of your time series. Imagine you have a very, very long time series. You can start choosing a subsequence length, and you can start comparing across the entire time series. And so this is what that compares. So if you choose in this case, we're choosing now a subsequence 4. So we're going to compare this part of the time series with this part of the time series. So basically these data points here, we're going to compare it with these data points. So they have to be the same length. And to compare this, it's not that complicated. If you know Pythagorean theorem, then you know how to compare these. And the most straightforward way to compare them is to calculate the Euclidean distance between these 2 points. So in this particular case, you have 4 points here, 4 points here. You take the first points, you subtract them and square them, right? Just like we would do in a Pythagorean theorem. Points, subtract them and square them. Eventually, you're going to see that the Euclidean distance between these two subsequences is root of 67. Now, this is pretty straightforward stuff, right? Hopefully, I'm not boring anybody, right? But really, where this gets tricky is now we think about calculating this for all subsequences. So we keep the first same, so that's in this green box, and then we just measure the first subsequence and we slide it over and we compute all of these distances. So obviously, when this green box is compared to itself subsequence, we have a distance of 0 because they're identical. And as we slide the box over, we get different distances, right? And that's only saying that, hey, we keep this green box the same and we slide it across. But that doesn't end our quest here. We actually have to now slide the green box over as well, right? And get the pairwise Euclidean distance. Oh, sorry, one additional thing. Going back to here, right? When you're the initial sort of pattern that you're looking for, or the initial subsequence with itself, you get a distance of 0, like no duh, obviously. So I'm not particularly interested. But what's interesting is trying to find which one of these sliding subsequences is most similar to what you're looking for, right? So in this particular case, what matches what we're looking for is this subsequence. This is the best match because it has the lowest Euclidean distance, aside from that self-match, right? So just keep that in mind, is that what we're really looking for is the best match, right, out of this entire subsequence. Now we can take this further. We slide our path across, and then we do that scan again, right? And then we slide it across again, right? And now we can speed this all up, right? We're calculating all of these pairwise distances. That's great, right? And then you end up with this type of matrix. So each row of this is, one distance profile, right? And the green box is sort of that lowest or closest match. This tells you what this is. This is good. There's a problem here, right? As your time series gets longer and longer and longer, this distance matrix grows and grows and grows, right? It's essentially n squared in size, depending on the length of your time series. And so if you can imagine, now we're running into constraints of memory, right? So running out of memory. And then number 2 is computation. Now it becomes very, very hard, and you need a very efficient way to compute this. We could do something different. Maybe what I said earlier is that we don't really care about all of these other distances. We just care about the closest match, which is where this green box is, right? So we're able to extract out all of those closest distance, and we extract something out called the matrix profile, which is just simply your nearest neighbor, right? What is the distance to your nearest neighbor for every single subsequence? And that changes the memory footprint to about O of n. And so this is good, but still, we still have to calculate this full matrix profile. This full distance matrix. Now, about the matrix profile out here, if I take all of these points here, right, which is your nearest neighbor, and I plot them underneath the original time series. So this is the original time series sequence up here. This is plotting it. And this is this matrix profile, which is just these numbers down here. By simply using this matrix profile, very quickly you can see and they're sort of aligned, right? So this distance is for these first 4 data points. This next Euclidean distance is for the next 4 data points, right? And it's trying to tell you for these 4 data points, its nearest neighbor is about 1.4 units away, right? And so if you look at this matrix profile, you can quickly extract two things. The first thing is that if you look at the global minima, which is here and here, right, these 2 points here, that means that two sequences, 1, 3, 2, 9, right, and 1, 2, 2, 10, are the closest, is globally the closest to each other. So this is like your global pattern that you're able to spot. And if you look at these numbers, they're fairly close. So this is a possible pattern in your data. And this starts to tell you that, hey, it repeats itself multiple times, that could be important to you, right? Now, on the flip side of this, the opposite end of the spectrum, we can look at anomalies. Are there any subsequences along my time series that doesn't have a particularly good match? And so you just look at the global maximum value, right? So this particular subsequence, 15, 1, 2, 2, the closest other subsequence is about a unit, I guess 14 away from it, which is very far away, right? And so this starts to tell you that, you know, these types of subsequences are unique, or maybe they don't really belong or are not normal, right? So you can very quickly extract not only the patterns, but as well as the anomalies. Now, the matrix profile alone allows actually many other things, and it's only the sort of backbone for this type of analysis. And explore the tutorials on the side here. We get through Stumpy basics, which into a more realistic example, but also there's things called like time series chains, semantic segmentation. These all come as a result of having computed this matrix profile. But here's the real problem. If we were to calculate that sort of n squared matrix that I showed you earlier, this is sort of the naive brute force approach where there's multiple for loops, just kind of looping through exactly how you saw the sort of sliding window scanning. And it turns out that if you had a time series that was about, what was it that we have here? I think it was maybe about 52 million data points in length. And how might you generate about 52 million data points in length? So basically, we're saying that for every minute, you're going to record some data. Maybe you have an IoT device, you record some data every 20 times per minute over the course of 5 years, right? That would produce 52 million data points. And if it took roughly, 10 to the minus, in this case, 10 to, I think, -6, -7 seconds to compute one of those distances, it turns out that it would take you just close to 1,600 days or 4.4 years to compute that full distance matrix, right? We don't have that amount of time, nor do we have 11 petabytes of memory to use, right? So obviously we need some better way to do this. Obviously this derived brute force, non-parallelized example, and that's really where Stumpy comes into play. I mentioned earlier that these researchers at University of California, Riverside, as well as University of New Mexico, actually came up with really nice math to simplify all of this. And it turns out that you can now compute this in a matter of days, right? And Stumpy brings all of that to you. And so we've reproduced all of that research work into a very easy to install package that anybody can use. Maybe I'll pause there for a second before I get into a quick live demo.
Yeah, I go ahead and bring up the live demo, and I think that it's really interesting. So it seems like a lot of this work is related, or maybe came out of the dynamic time warping kind of work. Is that true? Like the underlying concepts are the same.
Exactly. So that's very observative of you, actually. So the group that produced the matrix profile also did a ton of work in dynamic time warping, the same researchers. Now, dynamic time warping happens to be a much harder problem, because dynamic time warping typically is taking the entire time series, comparing one full time series to the entire times another full time series, right?
Right, exactly. Yeah.
In this particular, it is saying for time series, looking at sort of locally, are there patterns within one series? Or you could take two time series and say, are there patterns within time series A that exist in time series B, right? So it's more local than global. Although there are things that came out of this research as well to look at globally, to compare the entire time series by examining the subsequences within the time series. So if you have things that might repeat in one time series and all of them also exist in the other one, then maybe the distance between the full time series is similar too. That's a
Right.
great question.
Yeah. I have so many questions. So, but maybe we can get to your demo here.
Yeah.
Your live one.
Yeah.
Yeah, it's fascinating stuff. So
Awesome. So is it okay if I show this?
Yeah, go for it.
So maybe this is a challenge to
we only see the docs still. So if you're on another
okay.
Yeah.
Let me to
Yeah.
So just a quick question here. It seems like you could replace that Euclidean distance with any distance function if you wanted to work in sort of other spaces, right?
So actually, the short answer is no.
Oh,
that's an important question there, because by using
interesting
the Z, so earlier I said Euclidean distance, but it's actually a Znormalize Euclidean distance.
okay.
And the reason why they use that is because it happens to simplify the math significantly, and it allows for this computational efficiency to be had. So one must use the Znormalize Euclidean distance, and it's not without its faults either. But for the most part, it serves its purpose very, very well.
Yeah. Okay, great. Yeah. So let's dive into this demo here.
Yeah. So maybe I challenge people who are watching at home, and also if you're listening to the podcast later, make sure to visualize this and come back to the video. But at the top here, right, is a raw time series sequence of about roughly 10,000 data points, and this is exactly the case, right, where somebody or you might have generated completely new data, and this is what it looks like. If I told you that there was a pattern that existed in this data, maybe it doesn't exist. Can you spot it with the human eye? Right? And not to belabor the point, but it's actually very hard to do that. And even if I told you, right, this is the pattern that you're looking for, right, shown in green here. And I've blown it up, I've zoomed in on it. This is the structure of it, right? It's about 800 data points wide. Can you find somewhere along the top that matches this sequence? And I will tell you that it doesn't match exactly, but it's very, very close once I show it to you. And again, this is not really a big show you where it matches, right?
Right.
But it's almost one of those things where when you look at it, as you're scanning across, I've already forgotten what the original one looked like, right?
Right.
And so it turns out that the distance between these two time series is about a 9.2. It's not exactly 0, and it's obvious why it's not 0, because there are some differences at the end and some differences along the way. But for all intents and purposes, it's a pretty close enough match, right? And this is the matrix profile, right? So I've plotted here the entire matrix profile. And so for this green looking at, this is roughly the distance, right? So 9.2. And for every single sort of sliding window that we have, that closest distance to its nearest neighbor changes. And when I press play here, you'll see that it's essentially scanning across, and whatever the green box starts jumping around, right? That gray box starts jumping around. So whatever matches the green box could happen in the future. It can also happen in the past as well, right? And you notice that the distance changed dramatically, right? And we can even look at, in the case of the anomaly, which is, what sequence has a nearest neighbor that's very, very far away? In this case, roughly 26.7 units away. You can see that whatever matches the green pattern here is a pretty poor match. I mean, it's okay, right? But it's not exceptional either. So this matrix profile quickly draws your eye to, by looking at what the global minimum are, you can tell what the global pattern is, right? The close matches. But at the same time, by looking at the global maximum, you figure out what all the anomalies are, right? And by looking at local minima, you'll also find perhaps other interesting patterns too.
Right. So this is pretty. So in some sense, like it's not just about the shape of the pattern, right? Like the amplitude matters a lot for this kind of thing. So like just imagine, I guess, halfway through the time series, everything there was, you added 30 to it or something. That would then generate a distance or generate these matrix profiles that are like a lot larger than they would have been otherwise, right?
Another great question. So when we talk about ago, right, that we do a Z-normalized Euclidean distance.
Right.
What happens there is Z-normalized locally within a subsequence. So that means that even though if you have a jump in your data, because the two subsequences are normalized with respect to itself, this other one that's up here actually gets brought back down.
Oh, cool.
If that makes sense, right?
Good.
So that,
Yeah,
I think that's a very yes. That's
interesting.
Because typically with time series analysis, especially if there's an increasing trend over time, usually there's this concept of stationarity, right? Or non-stationary data, and that you have to sort of figure out how to normalize it either by subtracting or using some other methods. In this particular case, matrix profiles get around this problem because you're only comparing subsequences. You're not comparing the entire time series. So you normalize relative to itself, and then it brings everything back down. So even if our initial pattern that we had way back here, right? Even if this match, because it's normalized, we brought back down, and it will still match.
That's awesome. That's really nice. Yeah.
That's so
this has
cool.
been an incredible demo. Is there anything else that you want to show off, Sean?
No, I think this is a good place to probably move on.
Okay, great. Yeah, no, I certainly learned a lot during this demo section, and I'm confident our viewers and listeners at home will as well. So at this point, we're going to transition over to the roadmap section. So this is the part of the webinar where we get to talk about where Stumpy is going in the future and what the future holds for the project. And we like to contextualize this as these are places or parts of the code base where folks can presumably get involved and make contributions. And so that can either be in terms of software contributions, if you want to code, or if you happen to have deeper pockets and just want to fund Stumpy development. These are parts, things that the project is already going in this direction, and Stumpy is actively looking for contributions one way or the other. So
yeah, definitely.
Yeah, let's
so
take it.
We're definitely looking for PRs all the time. No PR is too minor, right? That's first and foremost. I think that not only do I appreciate it, I say very earlier on. I remember the first time that I was getting some, our repository. Bradley Dice from the University of Michigan here, who is a graduate student, helped me with a lot of the stuff, providing feedback. And one of them was, how to handle continuous integration. And so it was late at night, and I was submitting an issue for how do we do continuous integration with Azure pipelines. I have no experience in that. And by the time that I had finished typing it, somebody that I had never met before from Melbourne, Australia, who happened to be, I guess it was in the morning there for him, he decided that he was going to help me with it. He's like, I can hop on that. I'm like, cool. And then over the next 4 days, we banged out continuous integration in Azure pipelines. And then he left, right? And I was so grateful for this. And same thing with recently, another person came and helped us with adding a type annotation or type-ins, Python type-ins. And that was great too. So I really appreciate all those things. And these aren't even Stumpy users, right?
Awesome.
These are people who are looking to contribute to open source. But related to, more specifically, Stumpy itself, obviously documentation. If you see any problems or you'd like to contribute to the existing documentation, especially the APIs, if they could be any clearer, or adding some nice examples, that'd be good. But I think for now, from a performance standpoint, I think we're fairly happy, and it's fairly stable that you can use GPUs and CPUs, and it scales very, very well, and we work very hard to get there. But now I think what we want to do is to ensure that there are enough sort of tutorials and notebooks. So if you look at the current set of tutorials that we have, read the docs page that we have up. The tutorials are very verbose, purposely, and there's an interesting thing where I purposely reproduce those notebooks. Actually, are reproducing the examples that existed in the original papers, right? So that people can see that, can go and read the paper, and then get a little bit more, right? So it's like here's the idea of how you might analyze it. Well, here's how you would do it in Stumpy, right? And we explained a little bit more of the insights of maybe certain details of the matrix profile that comes out of it might be important, right? So and also the original researchers also are adding to this matrix profile ecosystem of many things that you can do in 10 lines of code or less. And so we're trying to build those out. So they have a list of like maybe 30 or 30 plus other things that you can do with once you have the matrix profile in hand. And so those examples I would love to incorporate into our documentation, right? So knowing that the matrix profile is already calculated, so what else can you do? Oftentimes trying to reproduce those research examples, the hardest part is actually finding the original data set, spending time locating that. And I have some ideas. Luckily, the original researchers also have a very nice sort of like a Google site for all of their projects where they provide a lot of that background, a lot of that code, and so we can reference. But what I've found that tends to work well for us is that when people want to submit either some small new code or a new use case based upon some of these papers, is I ask them to actually put together a simple tutorial notebook. So you don't actually have to tell me what's going on. Just write the task. Let's start off with that, right? And then we can go back and forth and review that and to say, hey, that actually works. And then we could add that color and that text to sort of fortify that tutorial. So the first thing is working on that on the code itself, right? But in addition to that, in the future, we're thinking more about performance. We're probably leaving about a 5x performance on the table still. And so we're looking to contribute to that in the future. But again, there are tons of things that the University of California Riverside have looked at, such as something called NP-dist, which is, I mentioned earlier, comparing time series, but also time series snippets. So given that you have these sort of subsequences that are, right, or that, how do you choose which one of those that don't look identically similar? Choose one that is representative of the group, right? And so these are all sort of interesting questions to ask that you can, now that you've calculated the matrix profile, you can compute these other interesting things.
Yeah, so that performance issue seems pretty interesting, especially for people potentially interested in funding the project. So what do you think, where do you think the biggest gains are that are currently available or can be made, or do you have a strategy for how to deal with that, or is it all kind of on the table, all options available right now?
Yeah, I actually don't think that the additional performance gains is going to be too hard. Again, luckily, the university, I've been in constant contact with them, understanding how their papers work, sometimes even helping to report bugs about the published work as well, right? And so we have an open line of communication, and so and the work is published, and we have some reference implementations that we can also look at as well. And so there's some low-hanging fruit that we can modify the code and update it. And again, we have unit tests. The output is given inputs of some time series, the outputs must be the same. So we know immediately if we've broken something. So there's really no fear here. So we can play around if we want to.
Yeah,
that makes some sense.
Yeah, so you kind of mentioned some of the additional tutorials that would be nice to add are, related to the things you can do that are based on the original paper and what you can do once you have the matrix profile. Is there anything, do you also, maybe I'm thinking of like a contributor, are you interested in having tutorials or examples that are domain specific? I know the package is domain agnostic.
Absolutely. I think that would be great too.
Examples
because
of how to
obviously
use
I don't
it in
know
a
everything.
domain?
I mentioned earlier, I'm not a time series expert, right? I have some experience with it, but I think it is having those examples out there sometimes just inspire or spark some thought in other people, right? And so finding those unique angles and being able to uncover interesting things would be fantastic. So I welcome all of the above.
Yeah, it's nice that you are interested in building out the examples and tutorials. I think that's really approachable for new users and for potential contributors.
Definitely.
It's a nice way to make your package robust.
Yeah, I think that's great. So is there anything else that you'd like to bring up in terms of the timeline, or sorry, the roadmap, or?
No, I think that essentially covers it. Obviously I want people to use it, and I would welcome any and all feedback, even criticism too. So.
Yeah, that's great. And just to reiterate, these are places where people can contribute, and that those contributions seem to be very welcome. So. Yeah, I think with that, we can go ahead and jump into our Q&A section. So if you have any last minute questions, please get them in now if you're viewing at home right now. And our first question today comes from Gurvinder, who asks, how to calculate the matrix profile of live data? My understanding might not be correct, but matrix profile needs the Z-norm Euclidean distance for all the past data. So is this possible to do something? Are there, I guess, real-time or kind of live applications of this?
So the great thing about matrix profile is that once you calculate it, right, for the existing data that you have, what you're storing is only the matrix profile, right, which is your nearest neighbor. So once you've captured that, if you have new data that comes in, all you're doing is taking that new subsequence that comes in, you compare it to the past, right, which is actually n squared. It's basically an order of n calculation, because you have one pattern that you compare it to everything else once, and then you stop. There's no sliding window of the initial pattern anymore. And when you compare that new subsequence to your original time series, and if that distance is smaller, you just update your matrix profile. So you can update it on the fly, and it's pretty trivial. So it's called MASS or MASS, which basically does that, and that comes in Stumpy. We currently do streaming yet, but that's probably a welcome implementation. That probably wouldn't be that much effort, I think, for anybody to help contribute if you're interested. Yeah.
Yeah, another contribution idea. I love it. Okay, so our next question is from Pero Peterson. Peru, so what would be a matrix profile of a random time series? Could one estimate the distribution from the matrix profile of random data?
Series? So if you randomness, assuming that let's say that the numbers are bound, between 0 and 1, right? If it's fairly random, then I would anticipate that the matrix profile would also look like noise, right? It would just be, straight across noise. And then the second part is, could one estimate the distribution? I guess the distribution of what? That's sort of unclear from the matrix profile of random data. I don't know about that. I don't know. Yeah, I don't know how to answer that question.
I think that's fair. I mean, it seems like this is a great. This would be a really great use of Stumpy. In fact, it's like you could just load in a time series that is random and see how they perform, right, and play around with it. I think that would be kind of a really interesting case to see and to visualize some of that data. So I have a question for you as well. So, and my question is, how do you determine the window length that you want to use for the matrix profile? What does Stumpy do that automatically for you, or are there guidelines for how to pick that? And sort of
yes, maybe I can share my screen real quick.
Please do.
So lucky for us, the original authors of these papers have addressed this themselves. So if we go to the Stumpy basics, right? So I mean, the short answer is this. Usually, so with Stumpy or with matrix profiles, there's really one parameter that needs to be set, which is the window length, as you pointed out. And usually what happens is, hopefully you have some domain expertise about your data, right? So if you're collecting, at least a little bit, right? So if you're every second, right? Well, chances are you're probably not interested. You might not be interested in year-long windows, right? You might be interested in maybe hours, days, right? But it turns out that if you look at one example, this is the Stumpy basics example, looking down here. So what the original researchers did was they looked at, in this particular case, this was looking at taxi of passenger rides, like the volume of, I think, half-hourly passenger rides. And what they did was, this is the matrix profile. They see that there's some sort of peak hours or peak days, right? And they happen to be, the anomalous ones happen to correspond to Columbus Day, Daylight Savings Time, and Thanksgiving, right? But there's a fundamental question of, because it's half-hourly recorded data, what is your... So what they show here is that if you make your window m equals 24, so I guess this is a 12-hour window, a 24-hour window, and so on and so forth. As you increase your window size, what you actually still see is that and this is the matrix profile for all, what you see is the anomalies, in this particular case, the position of the anomaly stays the same. You see this? So it stays consistent. Yeah. And same thing with the anomaly out here. It still stays consistent as you increase the data size. So as long as you're roughly within the ballpark, right, the window size actually doesn't matter that much, right? But also, the researchers argue that because you have a performant algorithm now, you can rerun it with multiple different window sizes, as you see here, and hopefully you can be drawn to where the anomalies in the pattern.
Yeah, that's fascinating. Well, I think we don't have any other questions loaded up here, so we're going to move on to our world famous rant section, where we each get 15 seconds to rant or rave about a topic of our choice. So first up, Sean, it is your soapbox.
Yeah, thank you. I'd like to sort of rave about the whole PyData and scientific Python ecosystem, but more specifically about organizers who organize PyData meetups and conferences and events, or other conferences and events. I'm actually one of the co-organizers of PyData Ann Arbor, along with Ben Zeitlin and Rose Butler, and we've been doing now, and I know how much work it is. And so I want to say thank you to all of the organizers who are out there in this sort of data science world. I really, really appreciate it. Thank you.
That's great, Sean. And also, as an attendee of a PyData Ann Arbor event, thank you. You did a really great job. Yeah, as a presenter, but an attendee, I attended Katie Huff's talk as well. And so thank you. It was really great. You do a great job too. Mine is not related to coding really, but some of you know my love of Europop, and related is synth pop. So I am going to leave you all with this great video I found this week of a band from the 80s where everybody is like kind of in very, I don't know, sober clothes, except the keyboardist who's wearing like a Hawaiian shirt and crazy sunglasses. And it's amazing. He looks like some like old man keyboardist Ron Swanson. So please enjoy. I love it. And I hope you're growing your love of synth pop as well.
Speaking of growing, for my my rave this week, I'd just like to say that I got an amazing beard trim this week when I was in California. I walked into a store that was simply called Barbershop. No one spoke English, so it was quite the experience, and it turned out great. So thank you all. That's all the time that we have for today. Thanks for watching. Thanks for listening. You can find us on Twitter at Quansight AI. If you're interested in funding open source projects, including Stumpy, you can find all of the project roadmaps at quansight.com/projects. Sean, where can people find you and Stumpy?
You can find me on Twitter at Sean My Law, and also seanmylaw@gmail.com. Look out for Stumpy. You can follow Stumpy at Stumpy_dev, or you can check out the Stumpy GitHub page. Or if you just Google Stumpy Python, it'll probably be one of the first hits.
Excellent. And join us again next episode for a Rail discussion on IBM Lail.